in terms of energy, the two pucks, we found that the change in translational kinetic energy, so change in K translation, was the same. And this is the change in a half m total v center of mass squared, because they ended up going from 0 to exactly the same speeds. But what we found is that the delta K rotational was different. And so there was a different, so therefore delta K total was also different. And the reason was that the displacement of the point where the force was applied was different. So here we're taking the system as the puck plus the string. The string has such a low mass that it's fine, right? But the displacement of the point where the force was applied was different. And so what we want to do is be able to write down equations that will help us analyze these systems this way and get information out of it. And what we're going to find is the following thing that's actually going to be very important. That when we talk about the change in translational kinetic energy, we're treating the system as a point. So we're saying Superman comes along, and he takes the puck and the string, and he compresses it down to a little teeny point that can't rotate or vibrate because it's a point. And we say, well, we apply the net force to this point, so we have to stick the force arrow there. And then we say that for the system considered as a point particle, the energy principle looks like this. The change in translational kinetic energy is equal to the net external force applied, the dot product of that times the displacement of the center of mass. And this is the energy principle, and the reason there aren't any other terms here is that a point particle can't do anything but translate. It can't rotate or vibrate or have internal energy. So that's what this is. The real system, though, is much more complicated. So this is delta E of the point system. For the real system, change of energy of the real system is certainly the external work done. And this is the change in the translational kinetic energy plus the rotational kinetic energy plus the vibrational kinetic energy plus any spring energies or something like that if we've got springs in the system, plus thermal energy, whatever we've got here. And but the work done isn't calculated that way because, as you saw, the little flag on the string actually moved farther than the center of mass moved. So we have to add it up this way. We have to say whatever force 1 is times the displacement of the point where that force was applied, plus force 2 dot the displacement of where that force was applied. So this is displacement. And by doing this analysis, we're going to see that we can actually get information. And these delta R's are not necessarily, in general, equal to the displacement of the center of mass of the system. And you saw that in the puck thing because the little flag moved a lot farther than the puck did with the one that was unwinding. For the one that didn't rotate, the flag and the puck had the same displacement, so that the force acted through the same displacement as the center of mass. But for the one that could unwind, the flag actually moved farther than the center of mass, and so we'd have to actually... So what we're looking for in these problems is different distances different distances that forces act through. And here's a simple example, and I meant to bring a spring in to show you, but suppose we take a spring. Okay, so here's our spring. It's unstretched. And we'll take the spring as the system. And what we're going to do is pull on this end with a force F and that end with a force F. And we're going to stretch the spring. Okay, so we get to here. So this is the initial state, that's the final state. Now let's just see what analyzing the system these two ways does for us. Okay, number one, well, since we're worried about the center of mass, we better find the center of mass here. So this is a massive, well, we don't care. Here's the mass of the spring can be 0 or non-zero. There's the center of mass. And then I stretch the spring, and the center of mass is still in the same place, right? Okay, so the delta x center of mass looks like it's 0. So let's do this thing. Let's do the point particle version. Point, the change in translational kinetic energy is F net delta R center of mass. So that looks like the change in a half mv center of mass squared is equal to, well, the net force is what here? We'll call this one F1 and we'll call this one F2, and they're equal in magnitude. So we have F1 plus F2 times the displacement of the center of mass is 0. But these two things actually add up to 0 also in our case. So we have 0 times 0, and it looks like the change in translational kinetic energy of the spring was 0. And that's right, because it didn't move, right? Okay, it was at rest at the beginning. But actually, I did some work. I pulled on this spring, and I exerted a force through a distance with each hand. So let's look at the real system. And what we're going to get here is that the real system, okay, change in energy of the system, and in this case, we have the change in kinetic delta K trans plus K vibrational, and there's some spring energy in here. That's K. Really, I mean, we could write down other terms, but they're mostly not important. And we know that, and that should equal it should equal F1 dot delta R1 plus F2 dot delta R2. And that's not 0. Because, so we have the change in energy of the real system. Okay, here's F1, and I moved a distance d here. So I have, that's the displacement of that, the point where I applied F1, right? So negative x component of F, but d is a negative number. Delta x is negative here. We move from 0 to minus 2 meters, something like that, okay? So we have F1d, and it's a positive number. Okay, over here we have an F2, and it acted through a distance d, and again the force is in the direction of displacement. So we have F2d, and so it looks like the change of energy of the real system is 2 FD. That's the amount of work that I put into this, to the real system. And what is this? Well, it's not translational kinetic energy. We know that because we already got that, so that's not it. It's not vibrating, so it must be the change in the spring energy. So it's a change in a half K sub S, S squared, 2FD. So the comparison of these two ways of treating the system actually gives you a lot of information. If you treat it like a point, all you can get is a change in translational kinetic energy of the system, but that's a very important piece. And now if we come back here and analyze the real system, we can use that result to say we know that's zero. We already worked it out, and so we can get information about other kinds of energy changes. Let's work a more complicated example problem, and then let's just practice a little with looking at distances. Yes? Well, okay, we don't actually, sorry, good point. Where do we get K vibrational? We don't from the analysis. We happen to know that it's not vibrating, but in fact, you're absolutely right. What we have to say is the change in K vibrational plus U spring is that, and without any other information, we don't know that that's zero. So you're right. Okay. Now we do from observing the system. So just thinking about the system. So other questions about this? Let's just work a sort of a complicated problem. Okay, this example's in the book, but I think a guided tour isn't a bad idea. In fact, there are quite a lot of examples in the book. So here we have a device that's sort of complicated. It's a box that has very low mass. It's got a spring in it, and then there's a clay ball of mass m. So this is a spring. And in this system, the box and the spring have very low mass, so almost all the mass of the system is in the clay ball. So essentially, the center of mass of the system is going to be wherever the center of the clay ball is. Okay? And what we're going to do is we're going to pull on it with a force F, and it's going to move. So after a while, we've been pulling with a force F. It's moved. And what has happened is, because we pulled on the box, and the ball, it took a little while for the spring to start stretching and the ball to realize it was moving. So what's happened actually, we've gotten to a point where the spring is actually stretched and the ball has now hit the end of the box. Okay, so we pulled some distance and just, so this is the initial state, and the final state is the ball has just hit the end of the box. And it's going to stick there. So let's see what we could find out here. One of the things we could actually try to find out is when the ball collides with the box, there's some thermal energy, because it's a collision and the kinetic energy of the ball, some of the ball's kinetic energy is going to end up being heat. So maybe we can figure that out. So what we're going to do is we're going to use this scheme, and I call your attention to section 8.5, where there's actually a detailed list of the steps you want to take in analyzing a system from these two different points of view, the point-particle point of view and the real point of view. And it's important to do all the steps because otherwise you get lost. So we need some distances. What are we given? Okay, I better be careful about this. There's a distance that we're going to call B. So we're going to use symbols, and then we could plug in numbers at the end if we wanted to. And that's the distance the front of the box traveled. Okay? And then there's a spring stretch S. So there's this distance S here, which is how much the spring is now stretched over from what it was before, from its relaxed length. And so the the distance that, so we can just redraw these arrows. So B would also be the distance from where the center of the box is now to where the center of the box is then. That's B. But that's not the distance the center of mass traveled, is it? Because the ball didn't go quite as far. So the distance the center of mass traveled is actually B minus S, as was just suggested. Okay, so now what we need to do is if Superman comes along and takes this big globby box and spring and ball and squashes it down to a point, we now have a point particle system. So the point particle system, we have the change in the translational kinetic energy is the net external force applied, dot product of that, the displacement of the center of mass, right? So we're in one dimension here, so it's all x things. So we have the change in translational kinetic energy. Well, we better draw a diagram. So here's our point particle diagram. Here's the point here. And there's a force F. And it goes a distance B minus S. So really the key part of analyzing this problem is figuring out how far the center of mass is, figuring out these distances, okay? Once you get the distances right, you've got it, and you can work the problem. But so the key part is, and to get distances right, you got to make diagrams or draw on existing diagrams, okay? You can't just eyeball it, it's going to be wrong. So this is the point system. That's our diagram for the point system. So we have F times B minus S, so they're both in the same direction, so the work is positive. And so that tells us the change in translational kinetic energy, and if it started from rest, we have a half m v center of mass final squared minus 0 is F times B minus S. Okay? Now the real system is a lot more complicated because the spring stretches and then there's some energy that's going to get dissipated as thermal energy. So the real system, we have the change in energy of the system is the work done by forces in the surroundings. And now we have to actually be careful. So that's the sum of any real force. So, well, we won't write sigmas, that's confusing. So it's the force times the displacement of the point of application of the force. And so here's the force here. The point of application of the force is here. That's the front of the box. It looks like the front of the box moved the distance b. So we have the change in energy of the system. Looks like for real, it's F times B. And that's the total energy of the system. So it's the change in K translational plus the change in, what other kinds of energy do we have changes in? Spring stretched, right? So we have U spring and we have E thermal, so delta E thermal. Okay. Well, which of these things do we now know? We know delta K translational, right? We just got that. So that's this. So we can plug that in here. So we have this piece is F times B minus S. What about change in spring energy? Do we know that? We know the stretch, don't we? So we know the stretch. So we actually know that. So that's a half k sub s squared minus 0, because it wasn't stretched at first. So we know that. Plus delta E thermal is F times B. So basically, I mean, these are the details, but the overview is that the total change of the energy of the real system is given by the real work done, every force through its displacement, and the change in energy, change in translational kinetic energy is the net force acting through the center of mass. We've done simple situations where there's only one force, relevant force acting, but there might be more. And one of the homework problems, the homework assignment is a sort of tutorial assignment in that it leads you through a set of problems. So the first problem, it really prompts you for every step. And you also get submissions by question by answer box, so you can get that part right. But pay attention to what you're doing, because the second problem has less prompting. So the idea is you should figure out the procedure you need to use on the first problem, apply it on as much help, and then the third problem doesn't give you any help. So by then you should need to really pay attention to what you're doing. Okay, so actually what we know, we can actually solve for delta E thermal in this case, right? So we get the change in thermal energy, the amount of energy that went into heating the ball in the box is F times B minus F B minus S minus a half K sub S S squared. And that looks like it's equal to, okay, F times S minus a half. So actually we got more information than we might have thought possible. Now what I'd like to do in the next 5 minutes is actually, first of all, do you have questions about this? Okay, let's just practice a little bit identifying distances and thinking about the structure of problems. And the questions we're going to look at, by the way, this video is actually on the web. So let's look at, this is actually a problem that's on the homework. And here's the situation. Okay, we have two blocks connected by a spring, and they're initially at rest. You might not be able to see the little numbers. The edge of the right-hand block is at 0.02 meters, and the left edge of the right edge of block 1 is at 0.02 meters, and the left edge of block 2 is at 0.04 meters. So these 0.02, 0.04, 0.08, 0.12. And we're pulling on block 2, and we pull for a while, and it starts to move, and the string stretches, and then the next block starts to catch up. And so eventually we get some sort of complicated motion where it's moving, but it's also vibrating. And so let's just practice identifying distances. Okay, this is 0.02 meters, that's 0.04 meters. Here, this is 0.08 meters, and this is 0.12 meters. And the question is, if you're going to analyze this system as a point, Superman crushes the system down to a point, what is that displacement that you're going to use for the analysis of the point particle system? How far did this squishy point move? 0.03 meters, 0.04 meters, 0.07 meters, 0.08 meters, 0.1 meters. Okay, 0.07, and that looks good. So let's look why that's right. The distance we want, the displacement we want, is the displacement of center of mass, right? So in the top one, the center of mass would be at 0.03 meters. And in the bottom one, the center of mass looks like it's at 0.1 meter. And so 0.1 minus 0.03 is indeed 0.07 meters. The center of mass moved that distance, so crushing it down to a point, and that point moves that distance. Here's the initial situation. It looks like the initial location was 0.03 meters for the center of mass of the system. It's in the middle of the spring. Over here, it looks like the location of the center of mass is 0.1 meter, because that's 0.08 and that's 0.12. So we move from here to there, and that's a distance of 0.07 meters. Okay, one more question, and this is an important one. How far, if you're now not doing point things anymore, you're looking at the real system, you're going to do the full complicated energy equation, okay, and its full complexity. What's the distance you use for how far the force acted on the real system? Okay, this is 0.04 meters, 0.02 meters, 0.08 meters, 0.12 meters. Yeah, awesome. All right. So actually, your hand, if you're pulling it, is actually moved 0.08 meters. So that difference, 0.07 meters, 0.08 meters, that F times the 0.01 meters, that's the energy that went into vibration, right? That's the work that you did that goes into vibration. Okay, good job.